Live.
A very good morning and welcome to all the delegates and the speaker for today for the fourth day of the QIP, 2-week QIP program. So today we are going to start a session with Mr. Muralidhar Anandamurthy. So he is an academic ambassador for JMP Global Academic Team, SAS Institute, India. He has 18 years of corporate experience in data science and statistical data analysis. His specialization are in statistical data analysis, data science, analytics, machine learning, designs of experiment, and he has various publications, national and international, on finance. He has presented various research papers. He also conducts workshops on data analysis using JMP, statistical discovery from SAS. With this brief introduction, I welcome Mr. Muralidhar Anandamurthy for his topic for today. So you can take over. Experimentation.
Thank you so much, Professor. So generous in introducing me. Couple of things. Please mute yourself if you're not asking a question, so that it helps others to listen properly. So we've been doing a lot of online from last couple of months. So what I'll do is to just save bandwidth. I'm muting my video also, so that you can see the presentation at the same time. You can watch me doing live on the JUMP platform. Okay, thank you so much again. Welcome to the session, chemometrics and multivariate experimentation. This is a vast subject, and I'll try to do justice as much as possible. And the focus would be, you're going to understand a little bit of chemometrics. I'm going to introduce to the concept of chemometrics, which is extensively used in pharmaceutical sciences. I assume that you people can hear me properly, and you can see my screen. Right, that's the assumption. If you feel any disturbance or problem in between, please let me know. And I'll also show some examples using JUMP, how JUMP enables statistical discovery, especially from pharmaceutical science perspective. And I will open it for the question and answers. That's the overall thought process for today. Okay, so probably you would have heard about artificial intelligence by this time. I know there was one session on artificial intelligence yesterday. And you've been introduced to the concept. I work for a company called SAS. If you know that company, you can Google it out. That's a 42-year-old company. It's the #1 company when it comes to artificial intelligence or machine learning or any kind of statistical data analysis. So we've been there from last 42 years, and I'm fortunate to be part of that company. So anything with respect to artificial intelligence or statistical data analysis, people whom you have to approach is SAS. And so just letting you know, we are the leaders in that space. So I'm trying to open up a concept called QSAR and QSPR. Probably most of you would have heard about it. The word chemometrics, if you see the diagram, it starts, the bigger circle is artificial intelligence, within something called machine learning and deep learning, and a subset of that is statistical data analysis, subset of that is chemometrics or multivariate methods. Essentially, everything is based on mathematics and statistics, I would say. If you ask me, did we had any word or a subject like statistical data analysis or else machine learning 20, 30 years back? Concepts were there, but the words were missing. Probably if you ask me data science, it came in last 5, 10 years, it has taken a lot of existence. So including pharmaceutical industries were using artificial intelligence techniques 30, 40 years back. It's all part of operation research or mathematics or statistics. Now with the advent of computers, people have started using more and more, and it has reached to the common man as well. When I say common man, the people who may not be a hardcore mathematician. So chemometrics plays a fundamental role in QSAR. QSAR stands for quantitative structure activity relationship, and quantitative structure property relationship, QSPR. I'm going to share this presentation with all of you. There are two methods, QSAR and QSPR methods, which aim at empirically linking the molecular structure of chemicals to the experimentally measurable properties. You know, you do an experiment and there is a property of a chemical, and then what is that measurable properties, how can you link that? That's where chemometrics comes into the picture. In fact, chemometrics, statistics, or chemoinformatics are the basic tools for finding meaningful mathematical relationship between the molecular structure or chemical or toxicological and environmental properties of chemicals. So pharmacy and chemicals go hand in hand. So the key element of QSAR or QSPR are molecular descriptions, which are numerical indices encoding information related to the structure of chemicals and are used as independent variables in the subsequent modeling. That's connecting QSAR approaches to the multivariate and chemometric. But I'm just trying to bring these concepts. If these are new to you, it takes a couple of minutes to understand. So you can always Google it out. It's easy to learn all these stuffs. So how do you relate quantitatively some of the properties and as well as some of the structure? Keep that in mind. You have a structure, chemical structure, and then you have a property. How do you mathematically link? That's what is QSAR or QSPR. The artificial intelligence is a bigger gamut. Within that, there is a machine learning or deep learning, and within that, we call statistical data analysis, everything. And then the chemometric or the multivariate method. So this is where we're going to touch base. So there are a lot of words which I might be using are interlinked. If I use multivariate, regression, AI, machine learning, everything is part of chemometrics at this point of time. Okay. So moving ahead. So chemometric, let's define chemometrics. Okay, so chemometrics is the chemical discipline that uses mathematical, statistical, and other methods employing logic. Okay, it involves mathematics, statistics, and other methods or computational methods, we call it as. What is the end output of this? To design and select optimal measurement procedures and experiments. Experiments is an important thing in pharmacy. We'll come to that in the later stage of our presentation, why we need to do an experiment, why you need to design the experiment and all. That's optimal measurement of procedures and experiments, and as well as to provide maximum information by analyzing the data. Data is everywhere, everybody knows. So how can we extract maximum information in minimum amount of time from the data? Data is as anything which you give a quantitative measurement to your observation, that becomes data. So this is a definition from Chemometrics and Intelligent Laboratory Systems, a leading journal. Okay, so you have data, just to summarize, and then you apply chemometric methods and you acquire knowledge. And if you ask me, hey, why we should learn statistics, just to give you, statistical thinking is no more a specialized skill in this world. It is an essential skill or a need. It's no more an I can take care of all the concepts, but I take help from a statistician for my analysis. Sorry, you cannot do that at this point of time. Statistics is something which, from an application standpoint, everybody should be aware of it. So that's the reason chemometrics plays a vital role in pharmaceutical science. So I might be using another word, machine learning. For me, chemometrics, machine learning, statistical data analysis, everything is same. How do you extract maximum information from your data? So looking at the chemometric techniques or machine learning or multivariate experimentational methods, either you cluster or segment. There are 4 different objectives when you do chemometrics. Apply chemometrics, when you teach chemometrics to your students. All of your professors, by end of the day, you also might teach these methods to your students as well. So cluster or segment is first thing. You examining the relationship with no intended response. For example, if I want to find out groups of drugs or the components or the patients that have similar properties, what are the techniques I can use? I can use a clustering technique or a segmentation technique. Or else, let's come to the next stage, prediction. So how do you apply prediction? Where and all you apply prediction? You want to find out the dissolution rate. What are the factors which affects the dissolution rate? There'll be milling, there will be coating, there'll be viscosity, there'll be pressure, there'll be temperature, pH. Which are those important variables which affects your dissolution? Dissolution is an important so-called output, so that you accept or reject the tablet based on the dissolution, right? So which are the important variables which affect the dissolution rate? So you start predicting. So use the existing data to predict future outcomes or the response in new situations. If I change mill rate, what is going to happen? Next is explain or describe. Not all the experimentation you would do for prediction, but you also want to do some of the experiments or data analysis for explaining a phenomena. So explain a relationship in terms of underlying factors that affect the response. For example, I just told you how dissolution can be increased or decreased by changing mill rate. I hope you are all familiar with the pharmaceutical manufacturing, secondary drug manufacturing process. So in this case, how if I change the viscosity, how it will impact my dissolution. You start explaining there is an inverse relationship or a direct relationship as a quadratic relationship. So you want to explain or describe, you start using chemometrics. Next is identify or screen. Find the important predictors or features, that is to reduce the number of predictors. For example, there could be 100 characteristics of a chemical compound and its productions are important for dissolution rate or assay values. Which are those 3 or 4 important factors? So you want to screen or identify those important factors. So you start using chemometric methods. So essentially clustering, you want to describe, you want to predict, you want to identify or screen. These are the end goal of a chemometric. You start using various statistical techniques to get onto this ultimate goal. Some of the chemometric methods. I wish I had all the day and resources to explain and show you all these things. But I'll choose some of these things and I'll show you today, but we'll discuss in our future conversation. You can always feel free to connect with me if you want to know what are the different chemometric techniques, especially used in pharmaceutical sciences. We'll try to cover majority of them, or prominent ones. So multivariate methods, which is the focus of today, principal component analysis, factor analysis, discriminant analysis, cluster analysis. We'll try to do each of these, we'll try to understand. And then do a little bit of multiple regression and predictive modeling. I'll try to showcase as a couple of cases on that. Descriptive, inferential, you're all familiar with it, probably model validations. How do you build predictive models? Okay, if I'm throwing a jargon, don't worry. It's just a matter of time. You start exploring this and you'll understand. It's so easy. Design of experiments, that's a big, I call it as a big fish, or as the unsung hero in analytics or innovation. Statistical process control, signal processing, time series analysis. There are a lot of methods. Am I going to show all of you? You won't fall asleep now if I start telling all these are showing. So I'll pick and choose and we'll try to do. And then we'll definitely meet. You want me to explain other things, we can always get in touch and you can connect with me. Okay, so JUMP enables, I've been using word JUMP, JMP. So it is pronounced as JUMP. I work for the SaaS company. JUMP is a product extensively used in pharmaceutical sciences, be it AstraZeneca, Salas Reddy, Sun Pharmas, you name the company, pharmaceutical company, all of them uses JUMP software. So this is a typical chemometric or classification of ML in machine learning or chemometric methods in pharmaceutical sciences. So why multivariate methods is one question you should be asking. So multivariate methods essentially help you to save time and effort and as well as reveal elusive patterns. So multivariate methods enable you to visualize, interpret and predict outcomes for many of the variables simultaneously while accounting for and making use of associations among those variables. So compared to univariate analysis, which is nothing but taking one variable and then analyzing it. So multivariate analysis can do multiple things at the same time. It can save time and effort, as I said, and you can unearth the insights from the data. So there are two methods are so-called categorized into unsupervised learning and supervised learning. So supervised learning, if you look at this, it focuses on classification and prediction. You will have one response variable, and unsupervised learning is more of a discovery and description. So JUMP has all these things as part of it. JUMP is a drag and drop, just like your graph prism or else your mini tabs or else design expert. Just drag and drop and you will start getting the analysis. That's where JUMP is positioned. So am I going to show all these things? Yes, may not be today, but in future. Okay, so historically, conventionally, how would you do? You take variables, do some design of experiments, and then do analysis. Okay, so you have multiple variables, do some experimentation, and then analyze. It takes a lot of resources, more time, and it is less efficient. This is the conventional way. What if you apply a chemometric or a multivariate methods? Called, you take the variables, apply multivariate and chemometric methods, and then you apply design of experiments. So this is more of an optimized way, which takes less resources, less time, and more efficient way. Okay, so that's why chemometric methods are extensively used in chemical and pharmaceutical industries, and it's been taught also. And if you see the research gate journals also, majority of them will be using principal component or else PLS, all those things. So we'll try to have a look at it. So while I said that I want to show all these things, but I'll not have time today, I'll focus on a couple of things today. To start with, we'll do the principal component analysis. Okay. So the purpose of principal component analysis is to derive a small number of independent linear combinations, so-called principal components, of a set of measured variables that capture as much as variability in the original variables as possible. Essentially, it is called dimension reduction. Okay, you have 100 variables. No, you can't analyze all the 100 variables. How can you minimize the number of variables or the dimensions, okay, or the parameters? How can you minimize by combining some of them into one or two factors or multiple factors or principal components? I use the word factors or principal components. So it is a dimension reduction technique. Okay, so it is also used as an exploratory data analysis, but we'll consider this as at this point of time dimension reduction. I'll try to show both of them. Okay, so let's take an example. Okay, so let me jump to jump. Okay, so where is my jump? Okay, so this is something which I'm going to use it today. So jump looks like this. Okay, simple, like just like a Excel spreadsheet, Excel sheet, or your any of your software if you have used it. Let me close all other windows. This is little tricky. Okay, so I've just made some hyperlinks so that I'm going to talk today about chemometrics and multivariate so that I can easily connect. So anybody can download Jump, JMB. This is a 30-day free trial is available. If you're looking at academic adoption, if your department or college wants, please connect with me. We do have an academic program where we give you unlimited license of this software. So principal component, I'll take this example of solubility. Okay, so this is a data set. Okay, this contains 72 chemical compounds. You can see this. Okay, methanol, ethanol, propanol, you can see this, right? 72 chemical compounds that were measured for solubility in 6 different solvents. So this is the solubility. You put it into a octanol, ether, chloroform. What is the solubility? So different solvents. So the first column gives the name of the compound. The next 6 columns gives the solubility measurements. How? So now that I'm going to apply principal component analysis here. So I'll go to analyze. If you look at this, this is design of experiments, all sorts of DOE, analyze. So I'll use the analyze method, and then see predictive modeling will use this multivariate methods. Look at multivariate methods. All these things are chemometric methods, including structural equation model, multidimensional scaling. So we'll use first, we'll check a little bit of scatter plot matrix, visually, let's explore the data. I'll use multivariate. And I'll say I'll put everything here, Y column, and I'll say I want to visually explore the data. Okay, this is how it looks like. Hey, there is some pattern, right? You can see this. Can you see some pattern here? Let me make a little bigger here so that you can see. Yeah, so you can see a little bit of a pattern here. There are some patterns which are kind of directly correlated, So I can see that, hey, looks like there are some dimensions which I can reduce. This is where I can combine some of the factors. Instead of 6 variables, I can combine them into some of the factors. That's why I'm going to launch principal component analysis. So let it be here. I can also see a little bit of correlation here. just to explore the data. So looks like, yeah, there is a lot of positive correlation. You can see this is a positive correlation. If it is red, it's a lot of positive correlation between some of the variables here. So looks like I can apply principal component analysis to minimize the dimensions. So I'll go here, analyze, multivariate, and then principal component. I can, and then I'll say I'll drag and drop all these things as Y columns, and then see it gives me a lot of estimation methods here, be it based on the correlations, based on the ML, robust, row-wise, pair-wise. Let's keep the default. So the default option uses either the row-wise, pair-wise, or ML methods. Jump also alerts you and recommends switching to wide method when appropriate. You need not worry when you're using jump, hey, which method to use. Jump will take care of it automatically. One thing I always keep telling myself is we need not be statisticians, right? We are all applied scientists. We may not be hardcore statisticians, and that's how jump helps. We need not be statistician. Even if I don't know anything, you go to help menu and try to understand how it works. How can I apply this technique to my experiment or my data? So here gives the principal component on correlation. Let's do a little bit of scatter plot we did. What and all. Okay, so let's try to understand a little more on the scree plot. Okay, so you can see this. There were 6 variables when we started, and your analysis shows. Let me take a little more. All these options are here: scatter plot, matrix, principal component, eigenvalues, and all. So let's see eigenvalues here. So 4.7, anything greater than 1 is considered to be a good component. And if you look at this, component 1, component 2, let me take some more outputs here. Bartlett test, eigenvectors, biplot, scree plot. Let's see score plot here. Okay, so it gives you a lot of outputs where you can see that 79.75, you can look at the 79.8% of the variation in the data is explained by component 1. And the second component brings a cumulative total variation to 95%. So this gives you 15% of the variation, and this gives you close to 80%. So instead of using 6 variables, I can use only 2 factors to explain the variation to an extent of 95%. This is what it's saying. This is, instead of using 6 variables, I can use 2 principal components. I hope you understood what I'm trying to tell. So I also want to show you a bit of visual biplot. I did biplot. I'll show a little bit of 3D plot also, 3D score plot. So this is how your principal component looks. Let me settings. Let me increase the marker size. Done. You can see visually how my principal component looks like. So it summarizes the variation of specified Y variables with principal components. You can switch an analysis based on covariance metrics or unscaled data by selecting principal components and whatever. So now that I did that, I can also launch principal component here or factor analysis here. Factor analysis for 2 factors, all sorts of variation methods are available here. And I'll say, okay, and then say, look at this, factor 1 and factor 2. These 2, if you look at this 0.91, 0.91, were loaded heavily to factor 2. That means octanol and as well as ether can be part of factor 2, while all other 4 variables can be clubbed into 1 factor: chloroform, benzene, carbon tetrachloride, and hexane. So these 4 variables can be clubbed into 1, and these 2 can be clubbed into 1. In your next analysis, you need not take 6 variables. You can reduce the 6 variables into 2 factors. This is called principal component analysis, or else dimensionality reduction technique. When you do an experiment, you'll have 100 variables, right? You cannot analyze 100 variables. reduce the dimension, reduce their variables, and then go ahead. This is one of the technique. Okay, so this is easy to do in jump. So now you saw that. So let me close this and then take another example. Okay, so that's a little bit of principal component analysis. Uh, Next is a little more clustering. We'll take a clustering example. So clustering is a grouping method or a classification technique. So group the similar variables into representative groups. Okay. So you can use cluster variables as a dimension reduction method again. Instead of using a large set of variables in the modeling, either use cluster components as the most representative variables. And that's what in an analysis we're going to do. So there are different clustering techniques available. Okay, so you can see this, instead of using all those, we can use a clustering technique. I'll take another example here. Let me take nominal mixtures. Okay, let me get back to jump here. Let me close. Here you go. I'll show you a clustering example. Typical cytometry example. So if you So cytometry is used to measure various characteristics of cells. I've taken a little more bioinformatics or pharmacogenomics kind of a data now related to pharmacy. So measurements of cell markers help to diagnose certain disease. Okay, so based on the measurement of cell markers, you go to diagnose the disease. In this example, we're going to cluster the observation based on the readings of the 4 markers in a cytometry analysis. Actually, cytometry analysis, JUMP has lot many clustering techniques. If you go here, analyze and clustering, you can see hierarchical cluster, k-means cluster, normal cluster, latent class analysis, cluster variables. I'm going to show you hierarchical cluster followed by normal mixture, both the things which I'm going to show you now. So we want to find out the clusters or the classification based on the variables behavior. Okay, so analyze and then say multivariate methods and clustering, and then say hierarchical cluster. So I'm going to add all these variables as my y, and you can see lot of options. Hierarchical, k-means, normal mixture. So I do hierarchical, and the methods are there, a lot of statistical methods. Don't worry about it. Whenever you have time, you're going to study that. And I'll say, okay. So now jump gives me the option, say how many clusters you want. You can see this. If I start moving, I need 6 clusters. There you go. So it gives me 6 clusters, and then I can also see what are the cluster variables. I'll show you a little more constellation plot so that you can understand what it is. Look at this. There are 6 clusters here. So this is one cluster, the green color, and this blue color, and this kind of a different color. This is another color, and this is another color. So these are all different clusters. So based on this, I can classify and then identify. So let's not get into the statistics behind this. It's simple. It works based on the covariances, whichever method you choose. So this is how you do. We can also see a little bit of 3D plot here, visually color map, and then let's see, yeah, scatter parallel concordant plots. You can see these are the 6 clusters and how significantly different they are from each other. So based on the markers, this is one cluster, this is a different cluster. You can see the values are different for different clusters. So you can, instead of taking all those variables, you can cluster them and then take it to the next level. So clustering helps you to classify as a classification algorithm as well. So parallel plot, let's see another another plot as excuse me, bit of scatter plot matrix. You can also see how it looks like. So you can choose whichever way you want. It starts giving you the plots. So you can see how different clusters are here from a marker perspective. You can see this. So this is more of a clustering. So I can also show biplot 3D. Let me show you biplot 3D normal mixture. So this I did a hierarchical clustering. I can also do normal mixture where I can put all these variables and I'll say okay. And he asks me how many clusters I need. I need 6 clusters, and I can go, say go. Okay, so it runs. You can see this. These are the 6 different clusters which are being classified, and the marker values are different for each of these clusters, and then they're statistically significant. If you look at the cluster 1, CD3 has 336, CD8 193, CD4 is 238 and 206. But look at the cluster 2 is different, even though it is closer to the CD3. But look at the CD8 values are altogether different. So this is how you start doing clustering, and the same visual appealing. You can see that. You can see biplot 3D. So again, three-dimensional, how clusters are visually you can perceive the different clusters. And what a parallel. This already I showed you, parallel coordinate plot. So this is a brief introduction to clustering, one of the dimensionality reduction technique. Okay, so moving on, so let's take on to the next one, clustering. Next is the discriminant analysis. The word discriminate should give you some idea. So discriminate or discriminant is nothing but a classification. Again, it's a classification algorithm. How do you classify based on the values or a continuous variable values? So for example, how do you classify people who pay tax, who doesn't pay tax? Just another example from a finance background. How do you classify or else identify based on some chemical component values? Hey, you measure 4, 5, 6 values of a component, and based on that you identify which component it is. That could be one way to apply discriminant analysis. You don't know, somebody has given you a component or a compound, okay, and then you measure 6 variables or 6 parameters of that, and then predict based on discriminant analysis. You can always do that if you have a historical data. Let's take an example of here. Okay, again, here is a data where iris data set. This is okay. So a researcher wants to determine the species of iris plants. Okay, based on the plant measurement, you take the plant and you measure sepal length or sepal width or petal length or petal width. All these 4 measures you calculate, and based on the sample, you have to predict which 3 different species they are. There are, you can see that there are 3 different species, Cetosau, Virginica, and versicolor. So based on these variables, how do you identify? If you get a new variable or new measurement, you put that into that model, it should say, hey, it should belong to this, it should belong to this. So it should help me to discriminate, at the same time predict which species it belongs to or which component it belongs to. I've taken a different example here just to show you. So let's get on to this analyze multivariate methods and systems. Discriminant, and these are all my y covariates, and my category is my x. Again, there are 4 different discriminant method: quadratic, regularized, wide linear, common variance. So let's keep this way, and I'll say okay. So how it gives you an output. Okay, so you can see, let me make it a little big here so that everybody can see. So now we can see from a discriminant standpoint, because there were 3 classes of species, you can see 2 canonical variables. So this is called canonical variables. It's again looking at each observation is plotted against the 2 canonical coordinates. So the biplot axis, it gives you a lot of options. See, you can see that canonical options, it gives you consider discriminant method, you can change, you can convert into stepwise. Okay, so this is your biplot canonical plot. So the biplot axis are the first 2 canonical variables. These define the 2 dimensions. You can see the 2 dimensions that provide maximum separation among the groups. See, you can see this is one species, and this is another species, and this is another species. You can see the color coding also. This is red, green, and blue. You could be doing an experimentation in pharmacogenomics, or else in your regular experimentation you want to identify, you can use discriminant analysis also. So how your algorithm, so it says that you can see this training data, 150 counts were there. The efficiency is 96% R square. You can see this. And then there are only 3 items which were misclassified. That means the analysis, the model is really good. If you want to see the model, you can save the model. Go ahead here and then save the discriminant matrices. All those things can be done. So discriminant scores, it will give you score options. You want to show ROC curve, you can see the ROC curve, how it looks like. So it doesn't make any difference here to look at discriminant. So this is again one example where it attempts to classify observation discrete by the value and continuous variable into groups. So it's called group membership defined by a categorical variable. So these variables are called covariates, and so X is predicted by continuous variables. So covariates are denoted by Y. It's different from logistic regression. I'm throwing another word, but this is just a classification algorithm which you can easily apply to classify your data. So it works on multivariate mean using Mahalanobis distance. Hope you have heard about Mahalanobis distance, how to calculate centroid and all those things. So that's part of a bit of 12th standard mathematics. You have, if you want to get into the in-depth of mathematics, you can refresh it up. So okay, so a jump is all interactive. I can show this. You can do a lot of analysis also while you want to do distribution, find out how normally distributed, all those things can be done before doing the analysis here. Okay, so this is about discriminant analysis. Let's move on. I'm just looking at the clock here. I might have to cover a lot many things. One last thing which I want to cover is partial least square. If you look at the ResearchGate, partial least square is extensively used, especially in spectrometric calibration. Okay, so we'll take partial least square and then get on to next multiple regression and then a little bit of design of experiments. So partial least square is extensively used when your number of variables is more than number of observations. In reality, when you do a lot of experiments, especially in pharmaceutical sciences, your number of variables will be more than number of your experiments or the trials or number of observations, I would call it. So when you have wide data where V is greater than N, okay, then you use partial least square. When you have a tall data, you use partial least square. When you have a square data, you use partial least square. When you have a noisy data, use partial least square. Partial least square is one of the best algorithm to apply for any of the regression technique or else your variable reduction technique also. So JUMP has 2 important methods, so-called NIPALS and SIMPLS, nonlinear iterative partial least squares and statistically inspired modification of PLS. Both these approaches are there. So instead of talking too much, I will try to explain with an example here. Okay, so let me take partial least square, and then I'll take, let me take what is a Baltic salt? Let me take Baltic salt. This would be a good one for you. This is a typical example. Partial least square regression models the response by explaining capability variability with both responses and predictors while maximizing the covariance between response and prediction. So if you have variability with both the X values and as well as Y values, use PLS. And you also see that number of observations are 16 here and number of variables is what, around 27. So you have more variables than observation, so use PLS. So this is an example with respect to spectrometric calibration, which is an area where partial least square is very effective. Okay, so the spectra of samples of seawater to determine the amounts of 3 compounds that are present in these samples. Okay, so there are 3 compounds. One is lignin sulfate, LS. It is, if you see this, this is LS, lignin sulfate, and then humic acid, HA, which is a natural forest product. Lignin sulfate is a pulp industry pollution. Okay, and an optical whitener, which is a whitener from detergent. I would call it as DT is a optical whitener from detergents. So the calibration data consists of 16 samples of known concentration of lignin sulfate, humic acid, and detergent. So emission intensities are recorded for 27 equidistant lengths. You can see the 27. Uh, Now you're going to use the partial least square to build a model for predicting the amount of compounds from the spectral emission intensities. In JUMP, it's so easy. Go to analyze, multivariate methods, partial least square. And I'll just put, these are all my Y variables. Sorry, my responses is this one. And all my wavelengths is my X factor. And centering and scaling, this is something which I would like to take another hour to explain, but I'll come back to you. Just click OK. So now it asks which method you want. So whether it is Nepal's or SIMPALS. So I'll say number of folds, K fold. I would choose none, and I'll say go. So number of so-called this VIP is nothing but so it gives you variable inflation factor in regression technique. It's just a variable importance here. So you can see a lot of statistics here. Okay, so we need not understand every statistic which a software throws. What is important for us? What does the percentage variation explain? If you see the number of factors, number of factor 1, X affects 97% and the cumulative X is 97%. So you can see this at least 2 to 3 factors. Instead of taking all those things, you can reduce the variability. And then you can also see from the other values here, number of factors, how it goes. Within one factor is good enough at this point of time, it looks like. So I can also do leave one out as a validation method, and then I can keep changing different validation methods. So that's a lot of things you can do with partial least square. So it's very effective. I strongly recommend if you're doing research, PhDs, or else putting a big research project, please explore these techniques. We're not going to get into the nitty-gritties of data. My goal is to give you visibility to all these things. How can you use this? Okay, so that is on a little bit of partial least square. And I can take another example of penta also, where I can show you the chain of amino acids. So each amino acid name is coded with single letter in the penta data example. Let me say this here. So I can model it. I fit a partial least square just to show you. Okay, so instead of taking all this, I can only take 2 factors and then I can explain all the variability. Instead of taking all these values, I can take only 2 factors. That's an example of variability reduction technique. Okay, so that's something on the bit of multivariate. I can go on. There are other multivariate techniques. If you see in JUMP, analyze, a lot of multivariate techniques are available here. Factor and multidimensional scaling, item analysis, structural equation models. But I'll just move on with some next version is something on multiple regression, and then have to focus on a little bit on design of experiments also. So this is a very famous example which the data set is available in JUMP. If you go to sample data set, JUMP has 600 plus inbuilt data set, which you can learn and then explore. Not at all a problem based on the kind of analysis you want to learn and the kind of category the data has been classified. So I'm taking a data from this only. So this is a typical secondary drug manufacturing process. Here is a dissolution, screen size, mill size, blend time, spray rate, coating viscosity, and all. So my goal is to predict what are the important variables which affect the dissolution. If you see that anything which is less than 70 dissolution, you're going to reject that. So that's the goal. So we want to find out what is causing lower dissolution. I just want to show a little bit of visualization before I get into the modeling multivariate regression. So JUMP has a lot of graphing capabilities, but one thing which I want to show is a graph builder. Let me explore dissolution first, and I'll drag and drop here. It gives me a little bit of scatter plot matrix. I can also put a little bit of, this is box plot, or else if I'm looking at histogram, I can see histogram here. I can put a histogram here. I can play around with. I can start over and I'll say I want to see dissolution with respect to mill time. Okay, just drag and drop. I will say, hey, looks like there is some kind of a direct relationship. I'm trying to make some, and I want to add with respect to blend time. I can keep adding this. Want to see with respect to spray rate, I can do that. I want to see with respect to coating viscosity. At the same time, I want to see with respect to mill size, what is happening. I want an area chart. I can do this. I can click here. I want a violin graph or a contour graph. All these things option. You want to fit a regression, you can see the regression also. So you can build your own graph with jump. It's so easy to do. Or else you want simple heat map, you can do this heat map. Or else I want a graphing from a 3D scatter plot. I can just see how my variables look like, and I can do a three-dimensional graphing capabilities also. So you play around with this and start finding out. I can apply any of the predictive modeling techniques here. Analyze, I'll go to predictive modeling and I'll say boosted tree, k-nears, all this supervised, unsupervised machine learning techniques are there. And I'll just do fit model here and I'll say, tell me what are the variables which are affecting my dissolution. I'll put all these things and I'll ask jump to go ahead and then do it. So it says that, hey, your lower dissolution is because of, or dissolution is affected by screen size, mill time, blend time, spray rate, and coating viscosity. I want to show something in jump which is called, and I'll say, oh, now that these are the important variables, I'll just remove all other variables. And I'll say, okay, these are the variables. Now I'll go ahead. There's something called prediction profiler. This is where you start predicting it. But I said that chemometrics also involves prediction. So now that you can see how each of the variables are varying. Yeah, somebody asked me, hello, sir, would you demonstrate 3D response surface plot? I would do that. I just saw the message. Okay. So now, you can see this, how once you change one of the variables, for example, if you start changing the mill rate, what will be the impact on on the dissolution as well, and what is the impact on blend time. You can start understanding the interaction. Somebody asked me response surface, we will do that also. With the same example, if I want to see the response surface model for this, and I will say, I'll choose all these things and I'll say, put my response surface and I'll say commit. So this gives me which all the important interaction also which are significant statistically. And then you can see mill time into coating viscosity or mill time into mill time. That's a quadratic interaction which will be which is important statistically. And you can also do bit of simulation here, Monte Carlo simulation. And somebody wanted me to show response surface, factor profiling, surface profiler, three-dimensional. This is what somebody was asking me if I'm right. Sorry about that. Okay, let me do a little bigger so that you can see this. So this is how your response surface looks like. Three-dimensional response surface with respect to mill time, blend time, dissolution. I can play around with this. So all these planes. Now this, you want to find out the optimal factor settings for your dissolution. You can go ahead and then ask jump to maximize desirability function, prediction profiler. Within that, you can ask jump to maximize desirability, and jump will give you the optimal factor settings for which can maximize your dissolution. That means jump is saying you use the screen size 3, mill time of this, blend time of this, spray rate of this, coating viscosity. You get a maximum dissolution, or else dissolution of 85% with a confidence band of 79 to 91. So this is one of the methods to optimize, and you can also run a little more simulation or a Monte Carlo simulation. It's very important. There will be some chemometric variables where you cannot actually test, they might be destructive, so that you use this virtual space of jump and then you can simulate the values also using exponential. I want to put an exponential for random blend time or else uniform distribution. I can simulate the values Okay, I can simulate the values. I can add a little more experimental noise and then simulate the data. Okay, and then say make a table, and it gives me 5,000 simulated values also. So you can go ahead and then simulate. This is part of QBD. Probably I take another session to talk about quality by design. QBD, when you take, how can you implant flexibility to the entire process instead of not only looking at end inspection. So extensively used as a QBD approach, simulation, and lot of things are there. And you look at the profilers here in JUMP, you can see contour profiler. You can see this also. Everything is interactive. So this is on a multiple regression. I'm looking at the clock. How much time I do have? So I have 20 more minutes or 15 more minutes before I open it for the question and answer, madam. Just looking at the clock. Meanwhile, any question at this point of time? Hello, sir, could you please demonstrate 3D response surface? Could you demonstrate predicted values along with experimental values in response surface plot? Okay. Predicted values along with experimental values. So, um, okay, so if I start looking at this, I will try to use another profiler here. Okay. So here is my contour profiler. I'll try to use contour grid. I'll use multiple contour frames, real time, and then take out, remove old one. Okay, so you have multiple contour grids, and I can also add contour grid of, okay. So you can see the screen size, mill time, blend rate, and this is the dissolution. Okay, this is the response. If I start moving, start looking at this, you can see the dissolution is also moving. All the mill time, blend time, spray rate, you can start playing around with this. So this is your optimal space, how it works in the contour profiler space. The same thing with respect to your three-dimensional also. You have to play around with this light, with the slider instead of the bar. Okay. So this is, but there are multiple profilers in JUMP which you can explore. One is this contour profiler or response surface profiler or interaction plots. All those things are there. When you take the mixture designs, especially the formulation design, I believe that somebody is talking about that in subsequent session, where you will have a three-dimensional or else so-called the quality space or design space or control space or knowledge space, where you have what are the constraints and then which is the exact optimal space or as the design space or the quality space you can identify visually also, or else through prediction profiler you can run an algorithm in the backend and then JUMP can throw you out those values. So that is also possible. So you can see this, you can play around with all those things and then find out visually. Okay, so that's a little bit of multivariate regression. As I said, everything is there, but I can't, it takes a little more time for me to show you. One last thing, bit of experimentation, which I wanted to show before I open it up for the question and answer. So design of experiments, JUMP has a robust platform for design of experiments. First thing is why experiment is very important. People normally ask this question. I thought experiments will help you to learn more. That means observe the concerted effect of multiple factors, capture the relationship between change in factor levels and response in a model. Theoretical models might be unavailable sometimes, or they might ignore real world effects. So you use experiment to learn more, and avoiding testing all possible conditions will help you to learn faster, and running a sufficient number of tests that would work together to answer specific questions about the variables will help you to learn efficiently. Then the question comes, why need to design an experiment? So there are three important benefits why you need to design an experiment. One is a control. So using a designed experiment is the only reliable way to measure a response to changing variables. So you'll have a lot of control. Estimation, designed experiment guarantees you learn something about what you want to know. So you can estimate. Efficiency, yeah, using a designed experiment assures you can learn the most from your data. That means maximum information from minimum number of trials. That's what minimum number of resources. That's why you need to design. So design methods on complexity. So number of model terms or number of factors, a lot of designs available. Okay, full factorial, screening design, Pluckett Berman, fraction factorial, orthogonal, supersaturated, definitive screening. All these things are in JUMP. Well, JUMP has all the classical designs available, be it your full factorial, box Jenkins. What is there in JUMP is there are two important designs which are extensively used in research and industry are called definitive screening design and custom design. I'll take an example. For example, my goal is to optimize yield. Okay, I have 6 factors: methanol, ethanol, propanol, butanol, pH, and time. And I want to estimate the main effects with two-way interactions. And I have only 20 trials. Okay, number of trials is also limited. In this case, none of your conventional designs would help you out. Our classical textbook designs would help you out because your restriction on number of trials also. If you look at the design of experiments, there are a lot of definitive screening designs, classical designs, all your mixture design, design diagnostics. What is something JUMP has is called custom design. If you look at my slide, the previous slide, fit the design to your problem, not your problem to the design. In reality, instead of taking what is available in the textbook or classical designs, you customize your design to suit your problem. Or else, as per your problem, you create a new design. That's what is called customizing, just like tailor-made solutions to design of experiments. JUMP has this called, it back in 2011, if you heard a person called Brad Jones. He is an authoritative in design of experiments, and he invented this, and he is part of JUMP. And this custom design platform and definitive screening design, both of them are in JUMP only. Excuse me. Extensively used in pharmacy, extensively research and industry. So I thought of showing definitive screening design. I'll take another time, but I'll definitely show you custom design now. If you look at this design of experiments, which go to the JUMP, DOE stands for design of experiments. There's something called custom design. So custom design, you add responses, whichever, whether you want to maximize, match the target, minimize. I say I want to maximize. My maximize is yield and have 6 factors, right? And I'll say those are my continuous factors. Look at this. I can add continuous factors, discrete numeric with levels, categorical factors with levels, blocking variables, covariates, mixture, constant, uncontrolled. You choose what are your factors. In our case, it is 6 continuous factors I will choose. Okay. So, and just keep these values and then continue. You can add as many as factor constraints, disallowed combination filter, use disallowed script, linear constraints, and you can also add main effects. Look at the interaction effects, second level, third level. You want to add response methods, you want to add power, you design. You want to add second level interactions, you get second level interactions. Now I want to add response surface, I will add response surface. Now that it also gives how many center points you want, how many replica runs, it also gives you an option of how many runs you can put. I'll say 20 runs. You can also put, and then JUMP goes back and runs an algorithm and computes a design, whether it's I optimal, D optimal, most efficient design based on your requirement, and then comes back with the design. So it's 28 runs I mentioned. So it gives me a design with 28 runs with all sorts of analysis. You can see color map and correlation. Mostly you can see orthogonality is maintained. With 28 runs, I can not only understand main effects, but also interaction effect, and as well as some kind of quadratic effect also. X1 into X1, you can see all quadratic effects also with 28 runs. This is custom design. I can go ahead and simulate the responses, make a table, and then say model it, run the model, and quickly see how my prediction profiler looks like. Okay, so this is on the design of experiments. Okay, we have come to the end of the session. custom design, which I mentioned, responses, you give the factors, you give the interactions, level, ranges, you choose powers, you choose constraints, choose center points, replica runs, and as well as number of runs. Let jump take run in the back end, and then it brings back the best design, efficient, most efficient design to you. And then you go ahead and do the experiment and analyze the experiment. Okay, so these are the books which I recommend to you. Discovering Partial Least Square, Strategies for Formulation and Development. Okay, this is, if you heard Ronald D. Snee and Roger W. Hurd. Snee is a big guy when it comes to consulting. He is part of big pharmaceutical industry. He consults to all the big companies. So he has written this book, very nice book. Then you can also go through Fundamentals of Predictive Analytics with JUMP. So as I said in the beginning, statistical thinking is no more a specialized skill. I recommend this to you and your scholars and your students. This is a free online course available. It talks about, it is built keeping in mind the requirements of industry, especially from a pharmacy background. People need to know statistical thinking, quality methods, decision making with data, correlation, regression, and as well as design of experiments. Very important. There are other two modules. Predictive modeling is also part of it. So you need to, it's a free course, online course, which is available on Coursera as well. And I strongly recommend this. Final thoughts. Statistical thinking is a need and an essential skill. It is no more a specialized skill in this world. Whether you work in BCom, commerce background, arts background, or engineering background, and especially science, it's a must. And we are all in the scientific domain, applied science, pharmaceutical science. So it is a need and an essential skill. So you want to learn, and some of you are already master of it. Congratulations. And if you're teaching, you start learn little more to teach better also. So chemometric techniques, reliable and valid results for your research and as well as for application one. It gives you quicker results. And because some of you might start teaching a little bit of statistical approaches in the classes. So teach to learn and learn to teach. And if you want to teach, please let us know. We are here to help you out. JUMP Academic team, we have the goal of orchestrating statistical and analytical thinking for department and universities. We are here to help you. And JUMP is a powerful and easy to use tool for pharmaceutical sciences. As I said, 600 plus universities are using, and the companies like AstraZeneca, Reddy, Sun Pharma, Merck, everybody across the globe, including the regulatory authorities, use JUMP. So some of the academic resources for you, go ahead and try out. 30-day free trial of JUMP is available. If you want to explore JUMP for your institution for research and teaching, don't worry, please connect with me. I'm available. So here is my phone number and email address. And as part of JUMP Academy program, we are also doing unlimited licenses of JUMP for academic adoption. In fact, we did had one of the series of sessions recently inaugurated by Dr. B. Suresh, the former President Pharmacy Council of India, where we had 6 webinars from foreign professors and authors on especially the pharmaceutical related stuff. So it has been there on the website also. I'll give you the link. So we do collaborate with professors and universities and help them to perform better, be it researchers, students, and professors. And please let me know. So there are a lot of white papers, books are available, webinars, resources are available. If you go to Google, it's all available here. So I'm just trying to show you. This is where jump.com is. You go to jump.com, jump/teach. Okay, so how we collaborate, a lot of resources, how to teach, how to learn for researchers. You can see this, faculties, academic researchers, and students. And if you're teaching, we are happy to help you out as well. Yeah. So JUMP for Pharmacy is also there. And so this is the website, JUMP for Pharmaceutical Sciences, Statistical Discovery for Professors, Researchers, and Students. If you see this, what are the different things JUMP can do, be it QBD, basic data analysis, statistical process control, stability, based on your ICH guidelines, how do you find out expiration date? So these are all the webinars which are already happened recently in Biostats, DOE, the recordings are available. Go ahead and then leverage. Any help, I'm here to support. Please let me know. So I'll stop at this point of time. I think we'll have 10-15 minutes for Q&A. So I was given 70 minutes, right? 70 minutes is what I've been allotted. So I think 11:10 is exactly 70 minutes at this point of time. I'll stop my presentation now. Let's open it for the question and answer. Thanks for your patience listening.
Thank you, sir. It's been a really interesting topic. Now we open for the session for questions. Can you take up the questions?
How to add discrete gradients in 3D response surface plot with a mesh. So
The questions will be read so you can address them.
Yes,
pardon?
The questions can be read to you. You can address them.
Okay.
So, how to add
Yeah.
discrete gradients in 3D surface plot along with the mesh?
So you're asking for something which is a graphical representation of data, right? So I can take that on a may I know to whom I'm speaking, Professor? Have you explored JUMP historically?
no, sir. This is the first time we are exploring it.
So what we can do is I can show you that, but first for that you have to download JUMP and then see we can do that. How can we do that? It's easy. Discrete gradients, yeah. So you have to in a 3D response. That means your axis you want to cut that, right? Based on you have to customize your axis in a three-dimensional response surface plot. Yes, you can do that.
Thank you, sir.
Yeah.
Any other questions?
So JUMP is very robust when it comes to visualization also. You can do many things with JUMP, not at all a problem.
Hello, sir.
Yes, sir. Go ahead.
Yeah, this is Dr. Anand Bandarkar from Goa College of Pharmacy.
Namaste, sir.
Namaste. Sir, I have one question. In case of discriminate analysis,
Discriminant analysis.
Yeah,
Okay.
you have taken an example of the 3 different species can be identified with their different parameters. You analyze the data, but how to interpret that data?
Interpretation. Interpretation is, so when you have a data like this, when you have a new data, new values. So now that you have built the model, discriminant model, what it gives you is a mathematical equation. I'll show you how mathematical equation looks like in discriminant analysis. So this is the data. And if I run a discriminant analysis here, I saved the script. Okay, this is how it looks like. And then if I look at this, scatter plot matrix, discriminant scores. Okay, where is this? Specify priors, consider canonical options, show mean. Okay, save discriminant matrices. Okay, we'll look at this values. Where is this? Where it is saving within shows. There you go. Here it is. Yeah. So if you look at the discriminant scores, it gives you a discriminant function, classification function. You apply the new values to it, it will show you which value it is. So now that I don't have a new value, what I'll do is after doing this analysis, I will find out one species and I'll calculate the value of sepal length, sepal width, and petal width. I'll apply those values to this discriminant function. Okay, to the formula, then it will tell you, hey, it belongs to Virginica or else Cetonsa. So based on some historical information, you interpretation is something like statistical interpretation is only classification. Here you are classifying based on this is an unsupervised or supervised learning where based on your responses, you built a model. On top of it, you are going to predict based on future values. So if you have a future, some values of sepal length or sepal width for some species, and then you put that into the model, it'll tell you whether it belongs to Setosa or else whichever species it is. So that's how you use it. Interpretation is, when you say interpretation of discriminant function, it's a combination of values, right? Group membership is defined by categorical variable and predicted by continuous variable. So it's a covariate and is denoted by y. So if you cannot interpret to an extent, so it's a combination of values. So it doesn't make any sense to interpret that function essentially. So it's a mathematical function, but using that you can predict further. If that answer satisfies your question, that could answer.
Yes, sir. Yes, sir. Thank you. Thank you.
Okay, thank you.
Anybody else?
Yes.
Any other questions?
So we can come to this concluding part of this first session. Thank you, sir. Thank you very much for coming on this platform to share your expertise. Being a grand ambassador of JNP software SAS, indeed it was a very good platform to take up this session of yours, where you have given a complete view of how the softwares can be used for reducing the time, space, and the resource material in coming out with an effective product. This has been viewed by many of the faculty members and even the research scholars. Many PGs have joined the session, and hope it has helped them, and we will come out with some commitments with the use of the software from our end. Thank you, sir. Thank you.
It's indeed my pleasure, Professor. Thank you so much from bottom of my heart for the opportunity given to me, and I look forward for any kind of support in future also. Please let me know, and I wish everyone a great statistical discovery in their research and teaching, and we are here to help you out. As I said, we do run academic program out of India. I'm leading that initiative. If you want JUMP as to be part of your college and your research, please let me know. Please get in touch with me. We are proposing unlimited license. That's the reason I'm in touch with Professor also. So we want every researchers and professors to be enabled statistically so that they can create impactful research. And that's where I feel when I go to ResearchGate, the people are applying advanced algorithms to analyze the data, and students and researchers should get hands-on dirty when it comes to these kind of advanced analysis, and JUMP is here to help you out.
Definitely, sir. This is the need of the hour.
Thank you so much, Professor.
Thank you. Thank you, sir.
It's a great talking to you.
So, sir, we request you to lead the presentation.
Yes, Professor.
Oh.
I'll share the presentation soon after this conversation. I'll send it to you so that students or the participants, you can share among the participants. I'm forwarding it to you, Professor.
Okay. Thank you. Thank you very much. So, for the participants, the next very interesting session by another eminent speaker, Dr. Satsaja Suresh, will be starting on time. And she's a very experienced member, research scientist, and academician who would be with you to join at sharp at 11:30. Please ensure that you join on time and interact to take the maximum benefit of the sessions that have been conducted. Thank you. Get back at 11:30 sharp. 10 minutes prior, you join. That would be better.